Hello, today we were going to do problem 11.4 out of fundamentals of heat transfer, and the problem reads as follows. It says a steel tube with K is equal to 50 watts per meter Kelvin of inner and outer diameter, D inner of 20 millimeters and D outer of 26 millimeters respectively, is used to transfer heat from hot gases flowing over the tube with a hot side heat transfer coefficient of 200 watts per meter squared Kelvin to cold water flowing through the tube with a cold heat transfer coefficient of 8,000 watts per meter squared Kelvin. The first question we're asked to answer is what is the cold side overall heat transfer coefficient UC? And then the second part says to enhance heat transfer, 16 straight fins of rectangular profile are installed longitudinally along the outer surface of the tube. The fins are equally spaced around the circumference of the tube, each having a thickness of 2 millimeters and a length of 15 millimeters. What is the corresponding overall heat transfer coefficient UC? So looking at our givens, we're given the thermal conductivity of the steel tube, which is 50 watts per meter Kelvin. We're also given the inner diameter and outer diameter, which is 20 millimeters and 26 millimeters respectively, as well as the hot side heat transfer coefficient and the cold side heat transfer coefficient, which is 208,000 watts per meter squared Kelvin. For the second question with the fins, we're told that we have 16 fins. They all have a thickness of 2 millimeters and a length of 15 millimeters. And we're asked to find two things. First, we're asked to find the cold side heat transfer coefficient UC for the case with no fins. And then we're asked to find the overall heat transfer coefficient with the fins. So our schematic is going to look like this. We have our pipe with our inner diameter and outer diameter. We have hot gases flowing over the pipe and the cold water flowing in the inside of the pipe. And the hot gases have a heat transfer coefficient of 200 watts per meter squared Kelvin, and the cold water on the inside has a heat transfer coefficient of 8,000 watts per meter squared Kelvin. Some assumptions we're going to make, we're going to assume that all the properties are constant. We're going to assume that there's negligible heat loss to the surroundings and kinetic and potential energy changes. We're also going to assume that all the surfaces are clean, so it's a new heat transfer unit with no fouling. And we're also going to assume that the flow is developed everywhere, so the heat transfer coefficient is going to be constant. So for calculation 1, our original equation is going to look like this. So 1 over ui, which is going to be our inside heat transfer coefficient, which we're solving for, times the area on the inside. And we're going to have these two units in here, this R double prime, which is going to be the resistance of the fouling. And since we're going to say that it's a clean heat exchanger unit and we're not going to have any fouling, we can go ahead and get rid of that. And then we'll also multiply this A inside, so the area of the inside over, and our equation is going to reduce to this. And with that reduced equation, we can go ahead and plug in all the numbers that were given. So we can plug in the heat transfer coefficients, as well as the radius of the inside and outside, and the thermal conductivity K on the bottom here. And we'll get a value of 0.004 approximately. And then we'll just rearrange that to solve for ui. And we'll see on the inside, or on the cold side, we'll get an effective heat transfer coefficient of 248.532 watts per meter squared Kelvin. So for the second problem, we're told that we add 16 fins to the outside to improve the heat transfer. And so the first thing we have to do is calculate the fin efficiency. We can do that by using this equation, or A to F is equal to tan H of ml over ml, where ml can be solved as the square root of 2 times the heat transfer coefficient on the outside, divided by the thermal conductivity times T, which is the thickness of the fin, and then multiplied by the length. And ml is going to solve to about 0.9487. So go ahead and plug in that value that we found, and we'll find that we have an overall heat transfer or fin efficiency of approximately 0.779 or 77.9%. The next thing we can do is solve for our overall surface efficiency, and we can do this using this equation. So we'll have this A to naught is equal to 1 minus AF, which is the area of the fins, divided by A, which is the total area, and then 1 minus our fin efficiency for a single fin. So we'll do 1 minus those area values. And then as we plug everything in, we'll see that we get a total surface efficiency of approximately 0.811 or 81.1%. We can then take this and determine what our effective heat transfer coefficient on the outside is going to become. And that's simply going to be our H outside, so our heat transfer coefficient on the outside, times that surface efficiency that we just calculated, times the total area over the original area, or just the area of the pipe. And we'll again plug in our numbers. So we have 200 watts per meter squared Kelvin, 0.811, our calculated surface efficiency, and then our areas here. And that's going to give us an effective heat transfer coefficient with the addition of the fins of about 1037 watts per meter squared Kelvin. So we'll now go back to our previous equation here, and we can go ahead and plug in that effective heat transfer coefficient on the outside for our resistance on the outside here. And we'll go ahead and plug in all of our numbers that we have. And finally, when we solve and rearrange, we'll now see that we have a heat transfer or effective heat transfer coefficient on the cold side of 1087.83 watts per meter squared Kelvin. So you can see that when we added those fins to the outside of the heat exchanger, it became a lot more efficient, and our heat transfer coefficient went up by roughly a factor of 4.